All right, great. So let's get started. So we're really happy for our next talker, Nico Döttling. It's going to tell us about pseudorandom obfuscation.
Right. Thank you, Daniel. Okay. So I'm not the first person at this workshop to introduce I/O. Let me do it anyway. Quick recap. Let's take two functionally equivalent circuits, and somehow people prefer the third binomial formula for two functionally equivalent but syntactically different ways of computing some formula. Anyway, let's take two functionally equivalent circuits. And what is I/O? Well, it's a compiler which takes a circuit and turns it into another functionally equivalent circuit, such that if the original, let's say if we start with functionally equivalent C0 and C1, then their obfuscations are computationally indistinguishable. So also a quick recap, currently the only, I would say, theoretically satisfying constructions we have of I/O are in this mold of JLS20, which really critically relies on some very evident algebraic structure, namely bilinear pairings, right? This is the sort of the main ingredient that fuels this construction in the end, or that's common to all works in this line. We do have, there is currently one alternative approach, which I will talk later a bit, what I call the BDGM20 paradigm, which, however, comes with a drawback that currently we kind of only have heuristic instantiations. But something that I've heard a lot in recent talks is I/O is essentially crypto complete, right? So whatever you want to do in crypto, probably I/O will let you do this, right? And for instance, right, this will by no means be complete. We know that I/O and one-way functions give us public key encryption, signatures, perfect NISICs, which actually turned out to be non-adaptive snarks, oblivious transfer, deniable encryptions. This was all in this one work of Sahai and Waters, fully homomorphic encryption, and witness encryption, right? And if we go a little bit beyond one-way functions and take somewhere statistically binding hashing, we get more advanced stuff like broadcast encryption, succinct garbling, and so forth. I'm sure I forgot a lot of work. Sorry if I forgot your favorite one. But I kind of want to challenge a bit, or I'm not the first to challenge this perspective that I/O is crypto complete, right? Some recent works have sort of looked at goals that are seemingly beyond the reach of indistinguishability obfuscation or even virtual black box obfuscation. And one thing that kept me thinking for quite a while until it was settled recently was this construction of doubly efficient private information retrieval, right? Where we now have constructions from ring LWE, but actually the same set of authors managed to show that obfuscation is seemingly or essentially useless, at least when we use it in a black box sense, how we're generally used to work with obfuscation. Yes?
Is the separation very different from the separation of I/O and the collision-resistant?
So that is, I think, I/O and collision-resistant hashing, this was only, I think, about polynomial hardness, right? Sort of, I think, I/O or sub-exponential I/O in one-way functions, I'm looking at Daniel, gives you.
It's also not from BBB, right? So like for BBB, it's easy to get collision-resistant hash, I think.
Yeah.
Oh, I see.
For BBB.
I see.
I mean, in the way I think about it, right, sub-exponential I/O gives you FHE, which gives you collision-resistant
I
hash.
think there they needed something more.
Oh, they needed more than?
Yeah.
Oh, okay, good. Then.
Randomizable encryption. That will give.
Oh, okay, good. Okay, then that was definitely a false bullet on this. Okay, good. Okay, but so there's other things that can be, or other seemingly simpler tasks that can be separated from I/O. Something very recently, this notion of pseudo-random codes, but we don't even have to go that far, right? Even if we go for more down-to-earth things like public key encryption with both pseudo-random keys and pseudo-random ciphertexts, we kind of don't know how to use I/O to build this when we don't put in assumptions that already give us this, right? So let's maybe quickly look into this, right? So how do I/O and pseudo-randomness relate? Now, in the secret key setting, building pseudo-random encryption is sort of the most standard thing ever, right? Kind of every natural encryption scheme you come up with has clearly a pseudo-random key, but also a pseudo-random ciphertext. And when we go into the public key world and take our favorite public key encryption scheme, El Gamal, also there, I mean, the public key here, here's not a private key, this is a public key, are just two uniformly random group elements, and under the decisional Diffie-Hellman assumption, also ciphertexts are pseudo-random. But now if we go a step further and ask ourselves let's say the natural way to build public key encryption from minimal assumptions in the world of obfuscation, the work of Sahai and Waters basically takes this private key encryption scheme up here and makes this tag pseudo-random. Right here, also the ciphertext is pseudo-random, but all of a sudden in the public key is now an obfuscated circuit, right? And if we get the guarantee that something is I/O, we cannot infer, okay, that there is no observable structure. The notion just is incompatible with producing pseudo-random outputs, right? So even if we take a very maximally unstructured function and obfuscate it, in general, we have to assume that this obfuscated circuit has structure, right? We cannot assume that this is pseudo-random.
Can we just use witness encryption, which follows from I/O, to get
So
pseudo-random ciphertext?
let's go one step back. Sorry, I would say no, right? Because now your ciphertext is a witness encryption. Now your ciphertext, basically when you build it from I/O, it's now an obfuscated circuit, and now you've just shifted. Now they switched roles. Exactly. So as whatever operation touches I/O now produces structured outcomes. Okay, good. So in general, producing or having encryption, I would argue having encryption schemes with both pseudo-random keys and ciphertext is something pretty desirable, right? For instance, this gives us non-committing encryption. Now probably Ran is looking suspiciously at me. So there is one scheme I'm aware of that builds non-committing encryption, actually based on I/O. However, the obfuscation is just shifted somewhere else. Instead of having it either in the public key or in the ciphertext, it's now in a common reference string, right? It's just the problem is pushed somewhere else. And one may ask now, does obfuscation intrinsically need to expose some sort of discernible structure, right? Or can it be pseudo-random, right? Is it possible that I have some circuit obfuscated and then this obfuscated object all of a sudden looks like a random string to me. And a few things that we've also seen in this workshop, there are some advanced encryption schemes from evasive LWE that sort of seemingly achieve this feat. I hope this is the laser. Oh, no, this is not the laser pointer. This is the laser pointer. For instance, this witness encryption scheme from Vaikuntanathan, Wee, and Wix, where we're getting, at least with a bit of care, I mean, by carefully analyzing this, witness encryption ciphertexts that look pseudo-random. And yeah, the question that motivated this work is, are there achievable notions of obfuscation which are sort of maybe not intrinsically at odds with pseudo-randomness? And in the rest of this talk, I'm first gonna introduce this concept of pseudo-random obfuscation, discuss a few applications in increasing level of surprisingness, so to speak, or I would say maybe applications that should make one increasingly worried, in particular when it comes to succinct witness encryption. And yes, once we're there, I'm actually going to discuss some counter examples to this notion. So this is a spoiler, and some alternative notions for this concept. And only then am I going to show you that it was kind of not surprising that these constructions from evasive LWE that we've seen have such strong pseudo-randomness properties. I will show you, or I will outline how to construct this notion of pseudo-random obfuscation from evasive LWE. Finally, if I have time, if I don't talk too long, I will show you more counter examples. But
is there, suppose I have a public crypto system, encryption scheme. Is there any separation between one that has pseudo-random ciphertext keys and one that does not?
You're asking whether, if you give me black box one, a generic public key encryption scheme, I'm not aware that someone wrote this up, but I think it's probably a bit more than an exercise, but this should be doable. Daniel, are you familiar? Well,
I don't know a construction.
no, I'm pretty.
Separation.
I'm pretty sure it should be separable.
I mean, construction would also be nice, but I suspect that it's separation.
I think Iftach Heiber's first paper was using a dense crypto system, which is a relaxation of pseudo-random, and he worked with it on DDoS and worked quite hard on trying to generically build it.
They failed. And they didn't separate it.
So, Mr. Sid, if this local mixing thing works, this will be
That's very good.
this is not the key. So
That's maybe the reason to study local mixing. Good.
random structure, random function, right? Cool.
But one has to be aware of the pitfalls that I'm gonna discuss in a bit. But okay, good. So the question we want to ask here is, can an obfuscation be of a circuit be unstructured? Or what are the necessary, maybe not sufficient, but necessary preconditions that have to be met? Right? Yeah, when could an obfuscation be pseudo-random? The first observation, a trivial observation, is that an obfuscated circuit always exposes the truth table of the underlying circuit. So if this function, or if this circuit C computes something that is not pseudo-random, we cannot hope to that its obfuscation looks pseudo-random, because we can easily, by evaluating this obfuscated circuit, always recover its truth table. And a second thing that needs to be paid attention is that when we're talking about pseudo-randomness, right, or a circuit computing having a pseudo-random truth table, we always talk about distributions of circuits. We're not talking about single circuits, but in this case, we have to think about distributions of circuits. And now, okay, let's assume we have some obfuscation scheme which produces random obfuscations, and then the question is, how does one evaluate a random program? Well, the thing is, we will have to sort of fix a machine model in the background, right, which I'm not gonna go too deeply into here, but machine model which accepts arbitrary strings as programs, right? If we have something like this, then an obfuscated circuit that will be an input to such a universal or potentially universal machine model will be a well-formed input. Okay, and now let's see with the notion that we came up with. I think originally we just called this pseudo-random obfuscation. I think after an iteration or two, this was called doubly pseudo-random obfuscation. And the idea is the following. So first off, let's say we have a circuit coming from some distribution with the guarantee that its truth table is pseudo-random, is computationally indistinguishable from uniform. Then we have an obfuscator, and we call this pro for pseudo-random obfuscation. And what we require is that if this precondition is met, then the obfuscation of this circuit is also pseudo-random or looks indistinguishable from uniform. I mean, typically, we don't just look at circuits that are pseudo-random by themselves, but pseudo-random given some context, right? Which is typically tucked away in such a in such a scrap bin called the auxiliary information, right? Which is information that's somehow related with this circuit, but we're requiring that even if for some auxiliary input, once the precondition holds, even given this auxiliary input, or once truth table looks pseudo-random, then so should the obfuscation here. Good, and this has also been discussed in prior talks. We will essentially only look at the exponentially efficient version of this notion of pseudo-random obfuscation, where we're not asking for full compactness, right? We're not asking that the obfuscated circuit is polynomial in the size of the original circuit, but just slightly sublinear in the size of the truth table. And henceforth, I will refer to this as the precondition and this as the postcondition of pseudo-random obfuscation. And in the following, let's for a moment, yes?
In the precondition, are you actually giving the distinguisher enough time to look at the truth table, or do they?
Absolutely. I said I'm mostly interested in this notion of exponentially efficient pro, where every algorithm involved has to expand the entire truth table. So yeah, but yes, even let's say in the standard notion that's not exponentially efficient, we have to give the distinguisher enough time to inspect the entire truth table. Good.
So, but then, sorry, you're saying so that has to be statistically?
No, computationally.
So like, right, if he looks at the entire truth table, which is so it's like you're starting to.
I mean, you can do complexity leveraging, or yeah. So I mean, but again, it's probably best to mostly think about this exponentially efficient notion, right? Good, but in the following, let's just assume we had this notion of pseudo-random obfuscation. What can we do with it? By the way, I have not yet said how this relates to indistinguishability obfuscation, or one might assume, oh, this immediately implies indistinguishability obfuscation. That is not the case. So the first application.
Sorry, that was the previous thing, the clarification. So in particular, a standard pseudorandom function does not satisfy your precondition, you say. So you need like a super strong, because the standard thing is only secure with one.
Yes, yes. So if you,
the precondition is very strong.
it is.
I mean, that's was more Woodish notion of a pseudorandom function. You cannot distinguish it in polynomial.
Pseudorandom truth tables, right? I think that's how we refer to this, as having a pseudorandom truth table. Good. Okay, let's talk about applications.
I guess you could generalize this, probably.
Come again?
I guess you could generalize it. I don't know if it would be interesting.
Sorry, now I'm clicking the wrong direction. Generalize it to what?
So you're talking about uniform, could be other distribution.
Absolutely, absolutely, absolutely. But as you will see in a moment, that already this notion here is problematic.
Okay.
So, good. Okay. So the first application is fully homomorphic encryption, right? And we do this by the recipe of Canetti et al. Let's say we already start with a leveled FHE scheme. This could be built from pseudorandom obfuscation, but let's just say we're having that already. And how do such leveled FHE schemes typically look? In the public key, we're having a sequence, we're having a key chain, right? We're starting off with a PK1, and then we're gonna get an encryption of SK1 under PK2, and so forth, right? Which sort of allows us to recrypt from one key to the next and do bootstrapping and sanitize ciphertexts, right? So given the first key, I can key switch to the second, to the third, and every time I do this, I'm reducing noise, right? And we know, or schemes like this are called leveled FHE schemes. And naturally, the evaluation depth for such schemes is bounded by n, right? I can sort of do n depth operations. After that, I'm sort of running out of keys. Good, and essentially all FHE schemes that I'm aware of do have pseudo-random ciphertexts, right? So what we kind of immediately get is that this key chain that we have here looks just like a bunch of uniformly random strings. So looking ahead, this will now already satisfy our precondition in a moment. But let's go back, and now let's say we have a long key chain, right? Let's say n is 2 to the lambda, then kind of we cannot write this out anymore, but we can compute these recryption keys locally and just have them produced by a small circuit, right? We can have a small circuit F, which on input I outputs the ith recryption key. And this is just a local computation, so this F will do pseudo-random things. But as I just said, wait a second, this sequence of keys here for natural FHE schemes that I'm aware of, this is already pseudo-random. So my F now satisfies this precondition I was talking about, having a pseudo-random truth table, meaning I can now pro-obfuscate it, and instantly, without doing any punctured PRF shenanigans, I can conclude from the post-condition that this pro of F must be indistinguishable from uniform, right? That's sort of an immediate application of this notion. But let's move on and talk about succinct garbling. Let's say we have some program P, let's say it's either Turing machine or RAM computation, and as we do it, let's assume it's represented by a sequence of step circuits, where the first one either has the input already hardwired or gets an input and state is passed on between these circuits, and the last one outputs a result P of X, right? To make this work, to make this actually compute Turing machines, we of course have to give these step circuits memory access, and I'm just going to assume that this access pattern that we have here is oblivious. So it's either fixed or random looking. So the memory is encoded with an ORAM or something similar. Good. So how can we garble such a computation? Well, we're starting with these step circuits. So the natural thing to do is to garble these step circuits, and I mean, for a reason that's that I'm going to show you in a moment, make it that the last step circuit outputs a share of the result, right? It doesn't just output P of X, but P of X, X or some, let's say, random bit. Good. Now, when I have this, I can just give you the other share in the plane, right? Now you can still evaluate this, just run these garbled circuits, obtain the output, and then XOR this share on top of the output, and you will have the result P of X. So this work of Brakersky et al. Showed that garbled circuits that are carefully implemented with this point and permute approach are actually pseudo-random or do look pseudo-random. They call this notion blind garbled circuits. So again, we get that sort of from the view of an outside observer who doesn't have access to this share here, this sequence of garbled circuit is indistinguishable from uniform. That's the reason we have this R here, right? Again, if R was not masking the output, then these guys together couldn't be pseudo-random, because evaluate them and let's say you're getting a structured output, so they're not pseudo-random. Okay, but now we're gonna do just the same thing as we did in the case of FHE. We just assume now, since garbling is local, that these step circuits are produced locally by a circuit that I call circuit factory, right? Or step circuit factory. So this circuit F here, you give an index I as an input, and it just outputs the ith garbled circuit here. Okay, so we see again the precondition is met. So let's obfuscate this circuit factory, and I'm now claiming that this these two things here together are now a succinct garbling of this computation, right? I mean, they're succinct. F was small, so pro F, let's say, is also small, and this additional share here is also small. So how can we go about showing that this is actually a good garbling scheme? Well, we already, now, next slide. The first thing that we're doing, I said this share R here is part of the description of this garbling. But when I give you this R, all of a sudden these circuits here don't look pseudo-random anymore. So what I can do instead of when I now want to use pro security, instead of having this R in the plane, someone can just give me these garbled circuits. I can evaluate them and X or P of X on top of it. And then I'm going to know that this is the right R. I've basically taken this equation here, evaluate the garbled circuits, and get P of X XOR, and I've solved it for R, right? So I can sort of just solve the output, since P of X is not hidden from my reduction, I can just solve this for R, And good. So this means I can recover this from the truth table of my pro of f. Good, but now if this R is out of the picture, I can again use pro security because these guys are looking pseudo-random, and that's the precondition, and by the post-condition, I can replace the obfuscated circuit factory with something uniformly random. And this is going to be my garbled circuit simulator, right? I'm just going to choose U uniformly random, and I can now derive these GC1 to GCN from my U and initialize some memory, evaluate it, and X or P of X on top. That's my simulator. I only need to know the output P of X to simulate, just as I want. So looking ahead, I think on Thursday, Giulio will show a much better approach how to get this notion of succinct garbling from succinct LWE, or an even weaker assumption called decomposed LWE. Good. Now let's go further. Now we're looking into pseudo-random witness encryption, and we're following the GGH RSW 13 recipe here. So let's first fix some NP language L and look at the following family of circuits. We're hardwiring a message, some NP statement X, and a freshly chosen PRF key K. So this circuit takes as input a witness W and does the following. It checks whether W is a valid witness for this statement X, and if so, it outputs M. Otherwise, it just evaluates the PRF on this witness W. Good. Having this circuit, we can just define our witness encryption as taking this circuit and running and pro-obfuscating it, right? Pro of this circuit is going to be my witness encryption, and to decrypt, I'm just going to take this witness encryption ciphertext, which is an obfuscated circuit, and evaluate it on my witness. And again, we observe that if X is not in the language, then no W will make the verifier accept, right? That means we're always going the second part, and we immediately see that C of MXK is computing the same function as PRFK, right? So again, my circuit C has a pseudo-random truth table in this case, and by pro security, we get that also the witness encryption ciphertext, namely the pro itself, is pseudo-random in this case, right? Follows kind of instantly. Good, but now, okay, pseudo-random witness encryption, this is already something we don't know from I/O, right? Or any other assumption, but we can go a step further, right? And get succinct pseudo-random witness encryption. So if we look at the construction from the last slide, the size of my witness encryption is a polynomial in the size of this circuit, because I'm obfuscating this, this circuit, right? The circuit has size of witness, many input wires, so I'm going to expect the size of this obfuscation to be polynomial in W. But as I've shown you, if X is not in the language, then this object, I mean, here I'm just going to write WE of XM for the ciphertext, is also pseudo-random, right? So for false statements, my witness encryptions are pseudo-random. So what I can just do is I can take a computation which just produces this ciphertext here bitwise, right? Let me define a function f prime of x and m, which this is a simplification, right? The actual construction is a bit more involved, but let's say it somehow manages in small space to just compute the ith bit of this witness encryption, right? The actual construction is, I think, going through randomized encodings, but if this is the case, right, if we can compute our witness encryption, even if it's very big in this case, then again, if x is not in L, this f prime of x comma m is again a pseudo-random function. And now the domain size is just log w, right? So in a way, or what I'm doing now is I'm sort of further compressing this pseudo-random object here, my ciphertext, into a small circuit that produces it. And good. And now my new witness encryption is just the pro of this circuit. I've shown you, I think this is not going to happen on this slide, but that if x is not in the language, then this ciphertext here is pseudo-random. So the truth table of this circuit here is also pseudo-random. So again, I can replace him with uniform, right? And decrypting this witness encryption is, again, rather easy. So first, I'm just gonna take this ciphertext here, which is just the pro encryption, and recover this C here by recovering the entire truth table. Once I have this, I'm just running this witness encryption on my witness W and recover the message M. And this is a notion that should make one suspicious, right? Because this is far out of reach of anything that we can do with indistinguishability obfuscation, right? So witness encryption or any kind of obfuscation where the description of the object that I have is far smaller than its input is out of reach of all our I/O techniques. And this brings me to issues, not just with constructions, but with this notion of pseudo-random obfuscation. So we've just seen that pro implies this notion of pseudo-random witness encryption. I don't even have to go to the succinct one. The important thing here is, since my witness encryption ciphertexts are pseudo-random, they actually hide false statements. If I have a false statement, it's gonna be hidden. This is not a feature of standard witness encryption, right? Standard witness encryption doesn't give us any kind of guarantee that the ciphertext reveals no information about the statement to which we are witness encrypting. And what I'm going to show you now is that the notion of pro is, in some sense, self-defeating in sort of the sense of Barak et al. And the basic idea is I'm going to put such a pseudo-random witness encryption of the following statement into my aux information. The statement is X is going to be, there exists some small circuit C such that X is the truth table of this circuit C. Clearly, this is an NP statement, right? And if X is long, right, one would generally not expect such a circuit to exist, right? Basically, this statement here says that X has small Kolmogorov complexity. Good. So my pseudo-random function is just going to be a PRF. And what I'm going to do is I'm going to expand the PRF into its truth table. And this X is now going to be my statement, or will give rise to my statement in this witness encryption here. Good, so precondition, I'm gonna have to make sure that this X here looks uniform even given this auxiliary input. I mean, first problem is the auxiliary input depends on X, right? So this is not just a trivial step, but recall what I've said a few moments ago, that we're gonna use some special feature of this pseudorandom witness encryption. The first thing that I'm gonna do is, well, X is a truth table of a PRF. So first I'm gonna replace it with some uniformly random string, but that means I'm gonna have to put the same uniformly random string here. Okay, this is a computationally indistinguishable step. But now let's look at this statement. It says U is the truth table of a small circuit. But U is now chosen uniformly, and I think it was Shannon's counting argument says for uniformly random U, no such small circuit exists that produces this U, so this statement here is false. Since the statement is false, I can use the security of my pseudorandom witness encryption to essentially replace this with a random string, but I'm gonna go one step further and I'm just gonna replace this string U by an independent uniform string U prime, right? There could be a step in the middle. I've just jumped over this. But now once I'm here, this witness encryption is independent of this string U, and I can now just reverse the first step, again using that truth table of X is pseudo-random, and I have established a precondition, right? I've shown that X is pseudo-random even given this auxiliary input. I had to sort of revert this auxiliary input back to its original state, right? That's what the precondition says, but now the precondition is established. Good, but now let's look at the postcondition. Recall that pro says if the precondition holds, the postcondition must also hold. Let's again take this string X, but at this time we're not looking at the string X itself, but at the pro obfuscation of this PRF. Auxiliary input is still the same. And let's compare this to the case where we've replaced this pro obfuscation by something uniformly random, right? The notion says, given this auxiliary input, these two guys here should be indistinguishable. But now let's just say this circuit here is now my witness, right? And what I'm gonna do is I'm just gonna feed this witness into my witness encryption, and I'm gonna run the decryption algorithm. Since this is now a small circuit that produces X, the witness encryption will have to output 0 to the lambda. Okay, on the other hand, when I take a uniformly random U, this is with very high probability not a good witness for this statement X. So, okay, here I wrote something, here I wrote bot, this should be something uniformly random, right? So in this case, my pseudo-random witness encryption should just output something uniformly random. But what that means is that we have a clear distinguisher, right? In the upper case, when we run this test here, we always see 0 to the lambda, and the second case, we always see a random output. Meaning that, yeah, for such contrived or self-referential examples, this notion of pro is not achievable, right? Because earlier I've shown you how to build this notion, just given pseudo-random functions from pro itself, right? So if pro for one auxiliary, this in some sense says if pro for some auxiliary input exists, then it doesn't exist for another one. But I see that I'm running pretty short on time. So what we did in this work is look at a weaker notion, which is implied by the stronger notion, but is also implied by indistinguishability obfuscation. So the precondition is still gonna be the same thing. We're asking that the truth table of such an F is pseudo-random, but if this is the case and I'm choosing two fresh keys for my F and run an IPRO, then they're indistinguishable. So the post condition now is essentially IO security even with unknown programs, right? Because I'm choosing these keys here randomly. Good. In a way, you can think of this as some notion of IO for pseudo-random function, and it is implied by IO. Therefore, we don't expect counterexamples.
So sorry, what changed from the stronger notion?
Oh, good. A stronger notion said I'm going to take a pro of this FK, and it's supposed to look uniform, right? Here, this was supposed to look uniform. Now I'm just saying the post condition is IO. So this notion is implied by the stronger notion, but it's also implied by IO. That's sort of the different, and since it's sort of anchored in IO, we're not expecting counterexamples against this notion. But
What is the quantifier over the keys?
good. Oops. What is the quantifier of the keys? They're just uniformly chosen. Yeah.
That's a tautology, right? It's a K0 and K1 and two.
No, I mean they're not those two.
With auxiliary information on K0 and K1.
Yeah, I've left this. But those two guys here, yeah, in the stronger notion, we have two notions, right? And one, they have to be functionally equivalent, two different keys for the same, that compute the same function, and another one where they're just uniform and independent, right? An intermediate notion. But okay, but why look at this notion? Well, even this weakened notion here, right? Give me this weaker notion and, okay, let me slow down a bit here. So the point is we will be able to construct IO or more specifically XIO for this notion. And the basic idea would be, okay, I'm gonna take my, let's say a circuit C that, any circuit C, I wanna build IO, and gonna mask it with a pseudo-random function, gonna pass this through XI pro, and I'm also gonna give you an XI pro of this PRF here. Only problem is this doesn't work, right? Because given this auxiliary input here, this function is not pseudo-random. So I'm gonna have to do something else. What we're doing is taking a pairing-based PRF that just, or a pairing-based pseudo-random function that just has a, let's say, quadratic stretch. And instead of obfuscating this, I just let you compute this from some keys that I'm going to give you in the clear. Well, this still doesn't work, right? But if I implement this PRF here just via a quadratic FE scheme, similar, I think JLS uses something very similar, I can actually make this approach work, right? Because when I'm using a quadratic FE scheme, I can actually simulate, let's say, ciphertext and secret keys together, given just the truth table of this PRF. But again, now I'm losing compactness, but I can recover this via an additional layer of amortization. And maybe the interesting, mildly interesting aspect about this is that this somehow follows or uses pairings such in the same way as GLS, but doesn't go through coding-based hardness, right? Sort of all JLS works that I'm aware of, they need to assume something related to LPN. And here, just assume this milder version of of pseudo-random obfuscation Now, okay, I spent a lot of time, and maybe I'm just gonna run over the slides here. So just as for I/O for Pro, it suffices to construct the exponentially efficient version. This can be bootstrapped similar to Bitansky, Vaikunthanathan, or Anand and Jain via the, let's say, the GGM tree approach, right? But my additional ingredients now are blind garbled circuits, something we know, and some new notion of laconic function evaluation, which we call blind LFE, right? Which also has this additional pseudo-randomness property. Good, but I'm just gonna briefly hint how does this BDGM approach that we're pursuing here work. So there one builds an I/O around a fully homomorphic encryption scheme. You give me an FHE encryption of a circuit C, and the first thing you can do is just expand it into its truth table homomorphically. Now, if this encryption scheme here is something like dual regef, an encryption scheme that has a small witness, right? You can think of this essentially as hybrid encryption. You have a sort of a short symmetric key which can be expanded into a longer mask. Then there is a way to sort of just recover this short key. And now, given this key and the rest of the ciphertext, I can just decrypt the truth table. Good, and obtain the truth table here. And my obfuscation, now the truth table is large, just consists of this encryption of the circuit, which is small, and this mass, or this key that I recovered here. Only problem is that this key here, in general, leaks information about the FHE secret key and therefore about the circuit C. So it's not that easy, right? If it was that easy, I/O would be sort of solved from FHE, but it's not. Sort of what the BDGM approach actually does, it somehow conjures a magic encryption of 0, somehow, uses it to re-randomize this encryption of the truth table, get a fresh encryption of the truth table, and then follow this recipe I was just mentioning. And now my obfuscation essentially consists still of the encryption of the circuit, this S here, but I also need this encryption of 0, right? And this is sort of where the heuristic part of all these constructions in the line of BDGM come from, because this thing is large. It's as large as the truth table, right? I mean, it's just an encryption of 0. It doesn't convey real information, right? But it has structure. It should be pseudo-random, but it still has to follow some structure because it's an encryption of 0. And yeah, I'm going to refer to this as magic ciphertext. But now let's recall that what we actually want to do is build XIO. So clearly, this encryption here, if the underlying FHE scheme has pseudo-random ciphertexts and pseudo-random keys, or random keys, which they typically do, then this ciphertext here is pseudo-random. This one here, we would also expect to be pseudo-random, but the problem kind of starts here, right? But what we can actually show is that if the truth table of my circuit C is pseudo-random, then this object here is also gonna be pseudo-random. And recall, this is not yet a good I/O, right? Because I'm giving you this magic ciphertext in the full, right? But I can show that just under LWE, if you give me these 3 things here, they will all look pseudorandom, conditioned that my truth table is pseudorandom. I'm quickly going to jump over LWE. Not a lot to see here, only that we're going to use that our errors are going to be in the smoothing regime, where they can just drown smaller offsets. Here, now the idea is, so why is this encryption here, why does it look pseudorandom? It's a dual regef ciphertext. They typically look like this. I'm just take a secret, multiply it with this large matrix, and add some noise. And one thing I can do, as before, is jumping. No, I'm not going to jump back anymore. But I can sort of just solve this decryption equation for this for this encryption here. Right, and taking all the other objects that I've seen, this S, encryption of the truth table itself, I'm gonna have an equation like this, where I'm gonna have, as is normal with lattice-based schemes, some leakage about the secret key of the underlying FHE scheme appearing in my error. Right, but this is where I'm using the fact that this error E will drown this out. I can make it disappear, and now I'm good to go. So first, I'm gonna replace this encryption of C with an encryption of 0, meaning also the truth table of C becomes a truth table of 0. And at this point, I can just use that my truth table is uniform and argue that this ciphertext here is uniform. And now also the S I'm going to give out doesn't leak anything anymore or also looks uniform. Good. This, in essence, I've cut a few corners here, establishes the precondition. But I still kind of need a mechanism to compress this magic ciphertext, because recall I said this magic ciphertext is as big as my truth table. And what I'm going to use here is a technique I like to call pseudo-drowning, right? And here we're going to use, this is the place where we're going to use this evasive LWE assumption. We're going to have a small LWE sample, and we're going to use this some matrix B inverse of P to expand this into a large sample. So let's take our small sample here, sublinear in the truth table size. That's good. And now we multiply it with this B inverse of P. And this gives us something like this, right? B times B inverse of P is just going to be P. So now we're having LWE samples, so to speak, with this weird error. Right? On the other hand, the heuristic of evasive LWE is that errors of this form essentially behave like fresh Gaussian errors, even if I know, even towards someone who knows this matrix B inverse of P. Right? I'm gonna, to make this work, I'm gonna again have to amortize sort of this matrix B inverse of P, but since I'm running really out of time now, I'm gonna skip all that. But an observation to be made here is that this E here has full rank, or it's Gaussian in the entire domain, whereas this thing here, only E is chosen Gaussian. This is a fixed matrix. I can see this matrix, so I know as an observer, as a distinguisher, that this error term here is in the span of this B inverse of P, and it sort of sits in a low rank subspace, right? But again, evasive LWE, the original version says that essentially, well, these two scenarios are indistinguishable, right? Give me this LWE sample and then a fresh sample here. Given my auxiliary input, they're supposed to be indistinguishable from uniform. This holds in the, this precondition is met in the, as I showed earlier for our XPro construction. Then it says also the post condition holds, namely this SB plus E looks uniform given this B inverse of P. Good, and the evasive LWE heuristic now says the only thing you can do with this B inverse of P is sort of expand these B sample and then essentially ignore this B inverse of P. And the noises in this subspace behaves like a fresh Gaussian noise term and can be used to drown artifacts, right? So essentially, we can use this not really Gaussian error to pseudo drown our artifacts. But again, what we've seen earlier is, well, once we got a pro from this, we arrived now already at a notion which has counterexamples, right? So we used evasive LWE to do something which we know is in general impossible, but in a follow-up work, what we did is we actually found I would say a direct and natural counterexample questioning this entire pseudo-drowning rationale, right? Because as far as I know, every single work that uses evasive LWE does pseudo-drowning. It uses this low-rank error to get rid of some artifacts that are floating around somewhere. Okay, so, but now I'm out of time, so I'm not gonna go through the second counterexample anymore, but since it really just fits on a single slide, this is a simple counterexample, and there's nothing contrived about it, right? There's really just linear operations happening here, and a reduction modulo 2, that's everything, right? Simple linear algebra is happening here, and that already gives us a distinguisher. Okay, so let me wrap up. Now, Pro is a really powerful tool to augment IOLA-like constructions with pseudo-randomness properties. But sadly, in general, it's too good to be true, as it suffers some counterexamples, right? In a way, on the way I see this, what it helped me to clarify for myself is this notion of Pro really exposed what was too much in the modeling of evasive LWE, right? Where did evasive LWE overshoot in its goal, right? By just giving us something that is this powerful. So we did propose this fallback, XIPro or IPro, pseudo-random obfuscation for, indistinguishability pseudo-random obfuscation, which does not suffer from counterexamples. And if you throw in standard pairing assumptions, SXDH, you can recover IO from this. Good, and yeah, looking what's to be done. Are there better notions of pseudo-random obfuscation that do not suffer from such counterexamples? Because I mean, the questions that I started with, right, getting like a generic way to augment cryptographic constructions with pseudo-randomness properties, I think that is still a valid goal. Right, and that concludes my talk. Thank you.
I think I might have missed a basic point. Like in your applications, where is the auxiliary input being used?
In most of them, it isn't. Right? It's I think the auxiliary input is used in the counter example. Good. So in the counter example, we have this auxiliary input, but in the paper, we even get rid of this auxiliary input here. So you can So if you're careful, you can actually put it into the function itself, right? But then Pro for circuits isn't enough. You first need to build Pro for Turing machines. But this is again something that works very similar as for I/O.
I see. So you could take aux out of the equation, and then like you still have a counterexample.
Yes.
Okay, got it.
But I mean, for let's say to go from from XPro, from the exponentially efficient version to Pro, we actually need the auxiliary input, right? So when you go from, let's say, weak compactness / efficiency to full efficiency, that's where the auxiliary input shows up.
Do you have applications of the weaker notion of this iPro, the one that?
It does naturally. I think. Soya, correct me if I'm wrong. FHE is implied by this. Also, do we get the succinct garbling?
I think so.
Yeah.
Like the version that goes to the space.
Yeah. So not the things that are outlandish, right?
So what is it? You get lossy stuff, or you get FHE? You get.
We do get FHE from
this, but
yeah.
If you go from level to unleveled, you still need to start with leveled, right? You
Yeah.
can build FHE.
Yes.
Right?
No.
Okay, let's thank Nico again. We have a break. Let's start at 3:30. Hey, what's up?